Contextual Hybrid RAG is a very powerful RAG strategy that combines the power of both contextual RAG and hybrid RAG in order to achieve optimal retrieval accuracy and response quality. And by the end of this video, you will know exactly what it is and how you can implement it yourself in n8n. So without wasting any more time, let's get right into it. By the way, some of you might have noticed that I already uploaded a video a while ago on this topic, but the difference in this video is that in our previous video, we implemented contextual hybrid RAG for Pinecone, and in today's video, I'm going to be implementing the same thing, but this time for Supabase. So if you're somebody that uses Pinecone for your vector database provider, then I would recommend you to watch that video, which I'm going to be adding to this card here. But if you're somebody that uses Supabase or any other providers, then you can continue watching this video. And the way I want to start this is first by explaining the different level of RAGs. And I want to start by first explaining what a traditional RAG is, what its strengths are, and then what its weaknesses are, and how we solve those weaknesses using contextual RAG. And then we'll also look at what the weaknesses for contextual RAG is, and then finally look at how contextual hybrid RAG aims to fix those problems, right? And for the explanation, I'm gonna roll in the clip from my previous video to save me an hour or more of editing. And after that, we are gonna be looking at how to set up this contextual RAG for Supabase, and then we're going to execute it. And finally, I'll walk you through step by step on what's exactly going on in each of these nodes. And if you already know what a contextual hybrid RAG is by maybe watching my previous video and also know what the differences between these levels are, then don't worry, I'm also going to be adding timestamps to the video so that you can just skip to the part where we start setting things up before actually testing this workflow. And so with that said, let the clip roll in. And let's start with traditional RAG. And traditional RAG is super straightforward, right? We have a document that we want to convert into a knowledge store or into a knowledge base. So what we would do is we would convert this document into chunks, and in this case, chunks of text. And then we will get that chunks and convert them into their vector representation, like the one we can see here represented in this diagram. And then we will just take these vector representations or vector embeddings and insert it into a vector store. And for those of you who don't know what a vector store is, it's essentially a special database that stores data within a high dimensional plane based on their semantic meaning. So you would have words like cats, dogs, mice being placed close to each other within a vector store because they're semantically similar, not because of the letters that they contain being similar, right? In this case, they are not similar in any way, but they are still positioned close to each other because of the meaning that they hold. So that is what a vector store is, and that is pretty much how traditional RAG works in general, and it is a very powerful strategy, right? However, while traditional RAG is great at fetching semantically relevant data, it is actually not good at fetching contextual ones. So let me actually explain to you with an example here. So our scenario here is a knowledge base that contains quarterly earnings reports for various companies. And let's say in our knowledge base, we have this particular chunk that says revenue grew by 3% over the previous quarter. That does not include any kind of context, right? We don't know, first of all, which company this is for, or which year, or even which quarter this belongs to. But let's say now a user query says, what was the revenue growth for Acme Corp in Q2 2019? Because the way that RAG works is by looking for semantically matching data, and again, because these two are similar, this one talks about revenue growth, this one also talks about revenue growth, so they are semantically similar, right? When we run this query in a traditional RAG, that RAG system can actually return to us this chunk here, which again could be from any quarter, any company, or any year, right? This would unfortunately cause our LLM to hallucinate, or actually it's not going to cause our LLM to hallucinate, but because it's being fed false context, it is going to refer to that in order to respond to the user query, and as a result, we get something that is not accurate. And so that is a problem with the traditional RAG system, and the way we solve that is by using this strategy called contextual RAG. And looking at contextual RAG, the way it works is very similar to traditional RAG, but we just add an additional layer to the way that we ingest data. So we have, again, our document, we split that document into chunks of text, And then after splitting this document into chunks of text, what we will do later then is we would actually combine each of these chunks with the whole document and then pass this document plus chunk to an LLM for it to actually compare the chunk to the whole document in order to add context to it, right? So for example, in our case here where it says revenue grew by 3% over the previous quarter, this was going to be the chunk. And in this case, our LLM would compare this chunk with the whole document, and it would be able to find to which company, which quarter, and which year this particular chunk belongs to. And it would basically create contextualized chunk out of that, which we are seeing here now. So we take in our document plus chunk, pass it to an LLM. The LLM basically processes this, generates a contextualized chunk for us for each of them, and then we do the exact same thing as we did with our traditional RAG, where we convert this one now here into its vector representation, and then we'll add it into a vector store just like we did for our traditional RAG, right? And when we look at our scenario, we have this improved chunk in the database. It is the same chunk here, but now it just has context added to it. So we're saying, hey, in Q3 2016, Acme Corp's revenue grew by 3% over the previous quarter. So when the user this time asks for what was the revenue growth for Acme Corp in Q2 2019, and because this time the database is going to return the same chunk, but with its context, the LLM will be able to compare it to the user's query and understand that this is not what the user is looking for. Therefore, it prevents the LLM from providing the wrong answer. And that is exactly what Contextual RAG aims to solve, and it does it very well. Actually, we are also going to be looking at that once I walk you through this workflow and see how that actually works. All right, so while we are now solving the contextual part of the problem by providing contextualized chunks to our LLM, preventing it from generating false information as a response, there's actually another problem that we are facing here, which you probably already noticed, right? In our query, we are looking for Acme Corp in Q2 2019, which is a specific kind of information that we are looking for within a knowledge base. This could have also been something like a product code, or let's say a model number for a mobile phone if you're trying to, let's say, troubleshoot a particular mobile phone based on its model, right? So in cases where we are looking for more specific data based on keywords like these, Acme Corp and Q2 2019, our query might actually return chunks that are like the one we are seeing here that is related to Q3 2016, for example. Again, Contextual RAG is at least going to prevent us from getting false information, but it is not going to guarantee us to actually get the relevant chunks when we query the database, right? So in cases where we want to, again, look for more specific data using keywords, product code, or again, model number of something, that is when using Contextual Hybrid RAG is actually going to be the ultimate combo that we are looking for. So for this, let's understand exactly how this works. And from this part all the way here, it's actually going to be the same thing, right? We convert the document into chunks of text, and then these chunks of text we are going to convert into documents and chunks, and then pass them to an LLM for each of them, convert them to contextualized chunks. And out of these contextualized chunks, we are going to convert it into dense vector embeddings, which is the embedding strategy for RAG, right? So we convert it to vector embeddings, and then we add it into a dense vector store. This part is basically exact same thing as this part. But now what's different with hybrid search, just like its name implies, we are also using another algorithm, and for that we are using another kind of embeddings as well, which is called sparse vector embeddings. And the logic under the algorithms that generate these kinds of vectors is actually based on keyword matching. So you can think of this as a traditional search where it's going to assign points to data based on the number of letters that repeat itself or the words that repeat within a sentence, right? That is in contrast to how dense vector embeddings work, or how RAG works in general, where we are actually storing data based on its semantic meaning. And so what we're doing here essentially with hybrid RAG is we are combining the best from two worlds, where we have semantically fetched data and also keyword based fetched data, right? And having something like this will just be very powerful for instances where we are looking for specific keywords. So what's going to happen is we are going to generate this dense vector embeddings out of our chunks, or out of our contextualized chunks in this case, but we are also going going to generate its sparse vector embeddings representation, and then we are going to store them separately in two different indexes. We have a dense vector store and we have a sparse vector store. And this was basically the storing part of things. The second part of this workflow is the part where we are actually querying data from our vector stores. All right, so first we have the query prepared, right? And this query gets converted into its dense vector representation and also its sparse vector representation, of which then we individually query against these two vector stores using the corresponding vector types. And after that, we get the accumulated results from both of these vector stores, right? So you can think of this as these two coming from the dense vector store, for example, and these two up here coming from the sparse vector store. After that, what we're going to do is we are going to pass these results to a re-ranker model such as Cohere. And this re-ranking model, what it's going to do is it's going to look at both of these results and look at the scores for each of these items generated by each of these vector store types and run an algorithm on it to re-rank the results for us. And finally, we pass it to an LLM, and this LLM generates response to us based on the context it received from our hybrid RAG system, in this case, to generate a much more accurate response in the cases that we just saw above. So now let's take a look at the exact same example again, and this time we also include the other type of chunks that may be present in the database, right? So we got Q2 2019, Q3 2016, and we got our same user query, and the result is Contextual Hybrid RAG uses both dense vectors to understand the meaning of the question and sparse vectors to match exact terms like Q2 and Acme Corp. This ensures that the system retrieves the correct chunk in Q, this one basically here, right? And this approach delivers a precise and contextually relevant answer, solving both the context keyword relevance problems seen in earlier RAG approaches. And that is precisely why having contextual hybrid RAG implemented in your system can actually be very useful. All right, so now that we looked at what contextual hybrid RAG is at a high level, we can start digging into this workflow here I have prepared for us. And I want to start by first setting up Supabase. And for that, what we're going to first do is we're going to head over to Supabase and get our vector store ready. And because I want to do this from absolute scratch, I'm going to start from creating a brand new organization. So let's call this RAG org. For the region, I'm just going to keep it as it is. And for the password, I'm just going to go in with a very simple password. Okay, it accepted that. I'm going to click on create a new project. Perfect. And now what we want to do is we want to first set up our database. And for that, we're going to head over to the SQL editor. And once you're in the SQL editor, the first thing we want to do is we want to run this command here, which is going to create a vector extension for us. So I'm just going to go ahead and paste this in here, then click on run. This is going to execute the command within the organization's database. And then the next command we are going to run is this create table command. And what it's going to do is it's actually going to create our vector store table. And so for that, I'm just going to go ahead and paste this one again. It's just that simple. So this command here is essentially creating a table for us within Supabase that's going to act as our vector store, in which you can see this column here called embedding, which represents our dense vectors. And also the number in here is actually the number of dimensions within the embeddings model that we want to use. And because in our case we are using OpenAI's text embedding small tree model, which has 1536 dimensions, we are adding that one here to accurately reflect that, right? Otherwise it wouldn't work. And the column here represents the full text search algorithm that's also going to be executed alongside with our, in this case, OpenAI embedding query, right? And then we got the content here, which is going to be the content of that particular chunk, and also a field that represents metadata, where we can add metadata of the chunks that we are ingesting for things such as file URL, file page, and so on. So what I'm going to do now is I'm just going to go ahead and execute this command as well. And you can see that this is going to create a table for us in the database, and that table is going to be called documents. And there you go, we got the table ready. And the next commands we are going to run are these commands here. The first one is going to create an index for the full text search. And for those of you who don't know what an index is in databases, it is actually a strategy that allows for efficient retrieval of rows within a database, especially if that database contains many records, right? So that's just what it is at a high level. So what we're going to do first here is run this first index, and I'm just going to click on execute first. All right, perfect. And the second column we are going to apply an index on is the embedding column, which is where we store our dense vectors. And so for this, again, I'm just going to copy this and go ahead and run this command again. Perfect. And the next query that we have here is going to be creating a function called hybrid search, which is what we are going to use whenever we want to search for something within our vector database. And you can see that this function here requires a text and then the embedding version of that text. And again, you can see here the number of vectors here represents our embeddings model. If you were to use another kind of model, you would have to change this number here according to the number of dimensions that model generates. Okay, and then we got match count, which is going to correspond to the number of items we want returned by this function from our vector database. And then we got full text weight float. This is basically telling how much weight we want to include for each of these algorithms. So we have one for full text search and also one for semantic search, which are both set to 1. And as its name implies here, it basically is going to determine the weighting for the results you get from each of these algorithms. So let's say you run a particular query, and for the full text search, the points you get for that query was 70, and for semantic weight you got for that query was 50, right? And if you were to set this number here to 2 instead of 1, what would have happened was that number you got for the semantic search would be multiplied by 2 compared to full text weight, which got 70, meaning that the value for the semantic search for that particular query would be higher. So these values are definitely something you can play around based on your use case. And the next parameter we have here stands for reciprocal ranking fusion, which is a smoothing constant, and it is going to make the algorithm decide how aggressively it should favor the higher ranking results when assigning points to it. And the higher this number is, or the closer it is to 0, the more democratic it is going to be, while the closer it is to 0, the more aggressive or the more exponential the difference that the algorithm assigns value to the higher ranking results compared to the lower ranking results will be. And so these are the parameters for this function. The rest of this are just the details which we don't have to cover. The only thing we'll have to do here at this point is just copy this function and then, or the query to create this function, and then paste it in our SQL editor. And once we do that, we can just execute it. And once it's successfully executed, we will now have a function that we can call whenever we want to query our vector store. And to find this function, we can actually look into, I think, the database, and within the database, we can go over to functions, and here we can just search for it. There you go. All right, so with this in place, our Supabase is almost ready, but we still have to do one last thing, and that thing is to create an edge function which we will connect to from our n8n, which in return is actually going to be the thing that connects or that calls this function that we just created and returns the results to us. Okay, and you can think of an edge function as an environment that Supabase provides us with in order to execute code on their end. And in this case, you can see that the code is written in JavaScript, and what we are doing in this code is we are actually creating an OpenAI client that we are going to use in order to generate the embedding from. So you can see here in this line, we are actually creating an OpenAI embedding, and you can also see the dimensions here, which is 1536. And so what we're doing essentially here is creating this embedding and then passing in our query, generating the dense vectors from it, and then passing that to the hybrid search function that we just created. And you can see that we are passing in the query and then the query embedding and also the match count. These are the parameters we were talking about when we were looking at the hybrid search query, right? You can see that that's actually what it's doing here. It's calling that hybrid search function and passing in the necessary parameters. And finally, it's returning the result it gets from this request that it sends to this hybrid search. And so again, what we're going to do is we are going to create an edge function, okay? And this edge function is what we are going to connect to from our n8n later when we want to query for data within our vector store. And we're going to be looking at all of that in just a bit. But before we do that, let's go ahead and create an edge function. So we are in the edge functions page, okay? And then I'm going to click on deploy a new function via an editor. And then I'm just gonna go ahead and paste this, and I'm gonna call this, let's say, I'll just call it query_db in this case. And before I deploy this function, I will also have to obtain an API key from OpenAI, which later I have to add into the secret section. Okay, so I'm just gonna go ahead and do that. I'm gonna copy this, and I'm just gonna go ahead here and then go back into the secret section, and then I am going to paste this as the value, and for the key I'm going to set it as OpenAI API key. And the reason to that is because when we go back to our function, oops, where is that function? No way, did I just close it? No way. Okay, let me just copy and paste it again. Okay, and then there we go. And when you look at our function here, you can see that it is going into the environment variables and it's looking for the value for a key called OpenAI API key. And what we did there in the secret section is basically saying, hey, the value for this particular key is what we pasted in, which was our API key, so that now when this line of code executes, this OpenAI API key is going to be the API key that we just added into our secrets. Okay, and before, again, I'm just gonna call this query_db one more time, and now I can just go ahead and click on deploy function. Once we do that, we should have our edge function ready to use, which is super cool. And when you do that, it's also going to generate an endpoint URL for you that you can copy from. This is the address we are going to use to send our query requests to. So I'm just going to go ahead and copy this, and the place that we are going to be sending this request is in this RAG querying section, where we're going to be sending requests using this HTTP request node. So I'm just going to replace my old URL with the one we just have set for our new edge function. Okay, and for the body, we are just going to pass in a JSON object with a field called query, and obviously pass in our query here. Now we actually got this part ready, but before we start querying our database, we obviously need to first ingest some data in it, right? So that's what I'm going to be doing now. And for that, let's just configure our Supabase node. So for this, we are going to go ahead and click on create a new credential, and then go into our project settings, I think, if I remember that correctly. Let me go ahead and see for API keys. Perfect. So we got the service role. I'll have to reveal this and copy it here. And then I want to go ahead and paste this one here. And the next thing we'll have to look for is the host URL. And let's see where we can actually find that. Is it in data API? Perfect. Okay, it's here. And I'll just go ahead and copy this and paste this one here. And I'll call this Contextual Hybrid RAG, and I'll just save this. Once we do that, we should be able to log into our organization, and there you go. I'm just going to go ahead and click on documents, and with this we can actually start executing this workflow. Once we're done executing it, I'm going to walk you through step by step on what's actually happening in each of these nodes. Just a quick heads up before we proceed, I will be uploading this template to the classroom section of my community. So if you want to get access to this and many other templates, feel free to check it out. And with that said, let's continue with the video. So I'm just going to go ahead and execute the workflow. All right, so now we are in the part of the workflow where it is contextualizing each of these chunks. So what we're doing is essentially we are hitting this LLM 33 times in this case, because our document contained 33 items. And this is basically going to run 33 times to contextualize all 33 chunks. All right, perfect. So the process is complete. Let's go ahead and check the table for it. Let's go to the table editor and click on the documents. Actually, before looking into this, let me show you the document that I've ingested for context, fiscal 2024. So the document that I ingested is basically NVIDIA's Q2 fiscal 2024 report, as you can see here. So this is the file that we are in a bit going to be searching from. Okay, now that we got this one out of the way, let's go back to the table. So we got our content column where we have the contextualized chunk. So you can see it says the chunk is the opening summary of NVIDIA's second quarter fiscal 2024 report. So this part here is the context for this chunk. And then when we look at the other one, it's the same thing. And then we got the second chunk here again with its context, right? Then we got the full text search column, which contains, like I said, the algorithm that it's going to use, or the data that the algorithm is going to use in order to calculate the points for each of the words or the query that we are looking for. And then we got the embeddings column here, which is our OpenAI embeddings dense vectors. And then finally, we got the metadata column where you can add all sorts of things. In my case, I actually added a file URL just to demonstrate how we can use it. You can see here we got the file URL for this particular document. So if somebody were to go to this URL, they would see the report here. So this is an example of how you can use the metadata column. Okay, so ultimately we now have the hybrid vector store ready, and with that out of the way, I can get to walking you through this node step by step so that we can understand what's going on under the hood. So without wasting any time, let's get right into it. The first node we have here is our Google Drive trigger. And basically what we are doing here is we're just setting a trigger that executes when a new file gets created. And in our case, we had this fiscal quarter 2024 for NVIDIA document that we wanted to parse, right? And once this executes, it goes into this loop node. And what we're doing here essentially is we're saying every item that is returned by this trigger. For example, if the next time this trigger gets executed, there are more than one file. In that case, you're basically saying for each of these files, enter this loop and just process it individually instead of processing them together. And the next node we have here is the set node. We are basically just extracting information from the file. So we got the file type, we got the file ID, and also the file title. Okay, and then we go into another Google Drive node, and in this Google Drive node, what we are doing is we're essentially downloading that file based on its ID. And you can see to the right, the output is the binary format of that file, which we later pass into the switch. What the switch node is doing here is just check the file type, and according to that, it's going to route the workflow accordingly, which in this case, our report was a PDF, and because of that, it routed the workflow through this route here on top. Okay, and from here we just extracted from PDF, and we got the data, and we converted that data into another set node with a JSON object that contains a field called data. And so that when we go into this node here, it can just say json.data when it wants to refer to the data from the previous node. At this point, we got the whole content of our document. Okay, and because we are using contextualized RAG here, what we have to do is we have to first split the documents into chunks by ourselves, because unfortunately, like I said, n8n does not provide a built-in way for us to implement contextual RAG. And so for this, what I did was I basically just wipe coded the code in this code function here, and essentially this works similarly to a recursive splitter. I even have the chunk size set to 1000 and chunk overlap set to 200. When you go to the recursive splitter that is provided to us as a built-in solution, you can see that there is this exact same thing here, right? We got the chunk size and also the chunk overlap. So essentially I built my own recursive splitter using this code node, and that's what it's doing. Okay, so it gets all of that, it converts all of it into an array of chunks using the recursive strategy. And then these chunks get passed to the split node, which basically splits all of these chunks into 33 different paths within the workflow. So you can actually see that here, which basically means that it's going to execute the next node 33 times, depending, of course, again, on the configuration. And that is what happens in this case. We have our LLM chain here. And for each of these chunks, we are calling this LLM once. And because we have 33 chunks, we are essentially hitting this LLM 33 times. And the inside of this LLM looks like this. So we got our prompt. We are saying, hey, this is a document. Okay, the whole document, we are passing to it. And then here is the chunk we want to situate within the overall document. We are passing in the chunk. And then we're also politely giving it some rules to follow when it contextualizes these chunks. And we are also telling it the format to contextualize them in. As you can see, this is what we were seeing in our database, right? So you can see that every chunk begins with this context, and the output for this is as follows. So I'll just go in JSON, and yeah, perfect. There you go. So we can see the first chunk. NVIDIA announces financial results for second quarter fiscal, etc. And then to the right, we can see the output of that. So we got the chunk is the opening summary of NVIDIA second quarter fiscal 2024 earnings report, and all the way here. And it's the same with every other chunks. So we got, again, the context, then just the rest of the content, and so on. It basically did that for all of it. And once we're done contextualizing it, this is another part where I implemented a trick in order to use n8n's built-in Supabase node here. And what I'm essentially doing is by collecting all of these 33 chunks and then combining them together using this custom separator here. And what this did essentially is create one huge as report again, basically bringing it all back together, but with these splits in between each of these chunks, which I can later strategically use in this Supabase node to chunk it accordingly. So when we go into our strategy, we can see here that, oops, sorry, not this, but this one. We can see here that what we did was we used a character text splitter, not a recursive text splitter. We're basically saying split this chunks or split this document using this separator here, which is the separator we used in the summary node, okay? And we also set the chunk size to 1200. This is also something you'll have to set strategically, right? It depends on the number of characters within each of your chunks. So when we go back to our code node, you can see here that I have a chunk size set to 1000 and chunk size or chunk overlap set to 200, totaling to about 1200 characters per chunk. And so when we combine all of these chunks together into a single document, we are using this character splitter then to say after every 1200 characters, look for this custom separator here and split the document according to that. And when we look at the result for this, it's pretty accurate. So it's a smart strategy. Let me just show you guys how it looks like. And by the way, we are also passing in the file URL, and this file URL, we get it from this set node here that we set from the very beginning, as you remember. So we're saying, hey, file URL metadata for this particular chunk is as so. And to the right, we can see the chunk. So when we look at the concatenated text, and then I'm going to do Control F and paste in the separator. And when I do that, you can see how the strategy actually works. So we got the whole chunk here all the way until the separator. And when we look at the chunk content, you can see that it's actually accurate, right? The chunk is the opening summary of NVIDIA all the way down to a new computing era has begun. And the next chunk begins from this part. This excerpt discusses NVIDIA's, etc. And then you can see it starts from here all the way down to cash dividends, just like that, all the way down until the end of the document. So this was my strategy to basically continue using n8n's built-in node for this. And with that, we have our document ingested. All right, so now that we are done looking at the ingesting part of this workflow, I'm going to continue with the querying part. And for this, again, we are going to be using a custom solution, just like we had to for the Contextual Hybrid RAG we implemented for Pinecone. But if you notice, in this case, this is much more simpler compared to what we had for Pinecone, which in that case, we had to run 3 separate HTTP request nodes and also a code node in between in order to prepare the payload. But in our case, because we already have an edge function set on our database, and it's going to be much easier for us now to just send a request from our n8n instance by just sending a single HTTP request to, again, our edge function, right? The URL of our edge function with this very simple JSON body where we pass in the query. And to connect this to our agent, what we're going to be using is this execute workflow node, of which, actually thinking about this in hindsight, we don't actually even need this for Supabase, since we are only using a single HTTP request node. So we can just pretty much connect a HTTP request tool directly to our agent. Alright, so I'm back with the changes, and as you can see, we have a much simpler setup compared to what we had earlier. And now the only thing we have here is a HTTP request tool node directly connected to our agent. And the only difference within the configuration for this node is the fact that we now have a description field to describe to the agent what we are using this node for, right? And in the body parameter, again, we have a field called query, and for the value, we are basically telling the agent to populate it for us. Okay, so with that, we are actually ready to test this out, and I have this query prepared from my previous video, so maybe we can actually start with that. And when we go into the document and look for that piece of data, we can see that it occurs here, and it only occurs once. So this is actually a perfect example. I can see why I chose this as one. So I'm just going to go ahead and execute workflow so that we can see what the outcome is like. So our agent returned a response, and when we look at the output, you can see that it says the phrase is related to NVIDIA's financial performance metrics for the second quarter of fiscal 2024. And when we look at the document, we can see that that indeed is the case, right? And this is actually not even surprising. Even using traditional RAG, the agent would have been able to respond it accurately since the document is pretty small. But what's more impressive is when we look at the results returned, we can see that the relevant chunk is actually ranked as the first item within the whole data set. And this would actually make a huge difference if you're working with a knowledge base that is relatively big. And Not only that, you could also save costs by being able to return less amount of data, since you're more confident that the first items or the higher ranked items are going to be the chunk that is relevant to your query. So that's another benefit to that. Now that we tested that out, we can also test something else as well. So I'm going to look for some other thing. For example, this number here, let's see if this is okay. This only occurred once, so maybe we can also try it out with this number here and see the result is going to return for us. So I'm going to save it, and then I am just going to go ahead and re-execute this workflow so that we can see the result together. Okay, perfect. We got our response, and when we look at it, it says the number 2473 within document is related to the weighted average shares used in per share computation. And when we go back to our document, we can actually see that that's exactly the case, right? Again, this is not surprising. I'm pretty sure you could even do this with traditional RAG for a relatively small document. But when we look at the items returned from our RAG database, we can see that, or we should see that this is going to be, again, the first item within the result set. So it is super powerful, right? And to demonstrate the difference, I'm actually going to run the exact same request, not even inside the traditional RAG, but directly inside this contextual RAG, so that we can see the difference. I'm just gonna make sure that this is mapped correctly. Perfect. Okay, I'm gonna run this and let's see what the result set is gonna look like this time. All right, so it just finished loading, and when we look at the response again, yeah, just as I expected, it was able to return, or at least respond with the accurate information. But when we look at the data returned by the vector store, right, I'm expecting this to not be in the first item of the list, and you can see that it indeed was not the first item in the list, but actually the third item in the list. And this is despite the document being relatively very small, right? Despite that, it came as the third item that is the most relevant to our query. And obviously the reason to this is because of how RAG works under the hood, which we already talked about in depth. So that's pretty much what the difference is, and how powerful having contextual hybrid RAG implemented can be very, very beneficial for you, especially in these kind of use cases. But yeah, with that, we are at the end of this video. I hope it was helpful for you. If you think it was, a like would be really appreciated, as engagement really helps with the outreach of my videos. And as I also mentioned earlier, I'm going to upload this template to the classroom section of my premium Skool community. So if you want to get access to this and many other templates, you can head over to my community. Definitely check it out. Once you're in, you can just head over to the classroom section, and in the classroom section, you can head over to all my builds. And in this case, we're looking for contextual hybrid RAG for Supabase. So you can just head over to this section and then scroll all the way down, and at the bottom you'll find the template attached as part of the resources. Once you're here, all you'll have to do is just download it and then go over to your canvas, click on this button here and click on import from file, and you should be good to go. But anyway, with that said, I hope to see you inside. If I don't, I'll see you in the next video. Have a good one.